Welcome to solverfy.
Here, an object with a mass m was accelerated by a compressed spring. So I'll draw the initial state of this task. So that's compressed spring. Which accelerates which has some kinetic, which has some potential energy. So potential energy of the spring equals to k delta x squared, where delta x is a deformation of the spring. Then the spring was released and it pushed the block to the left, and the block had initial velocity of v0. Then after some time, after the block had been released, it traveled for 8 meters and stopped. So here the velocity is 0, and this is the displacement L. So first of all, we have to calculate the acceleration of the block when it's slowing to stop. Let's do this. Acceleration of the block will be controlled only by the friction force. And for example, for some middle position here, this friction force equals to N, which is the reaction of the surface, times friction coefficient. So basically, acceleration of the block equals to the vector sum of friction, reaction of the surface, and the gravity. And if we introduce y and x axis, then and if we project acceleration onto the x-axis, so basically we get the following: negative acceleration equals to negative f, and on the y-axis n equals to mg, and also friction force equals to friction coefficient times n. Now this all being said, here I forgot ms. Ma equals to mu mg, and acceleration equals to friction coefficient times g, which is 0.20 times 9.8 meters per second squared. Let's calculate this number. It equals to 1.96 meters per second squared, and if we round to 2 decimal places, that will be 2.0 meters per second squared. Okay, now we have to calculate the object speed when it leaves the spring. So we have to calculate v0. Work of the friction force, absolute value of the work of the friction force, equals to the difference between initial kinetic energy and final kinetic energy of the block. And the final kinetic energy of the block is 0 because it stops. Then it equals to the initial kinetic energy. Then, on the other hand, absolute value of the work of the friction force equals to mu mg, which is the friction force, times the displacement d, where, here it's labeled as L. Yeah, L, that's a distance traveled by the block, which equals to mv squared over 2. Then V0. Then the V0 equals to the square root of 2 mu GL. So it equals to 2 times 0.20 times 9.8 meters per second squared times L, which is 8.0 meters. So let's calculate the number. It equals to 5.6 meters per second. Okay, that's done. Now we have to calculate how far the spring was compressed. So to do this calculation, we have to calculate the initial potential energy of the deformed spring. And I'm sorry, having some. Yeah, the initial potential energy of the deformed spring equals to kinetic energy of the block, basically before its release, when it's released, and it equals also to the work of the friction force, because all the initial potential energy is transformed into the work of the friction force. So then K delta X squared over 2, yeah, and here we have to calculate delta X. K delta X squared over 2 equals to mu mgd. Then delta X equals to the square root of 2 mu mgd divided by K. Now we can calculate it. So it equals to the square root of equals to the square root of 2 times 0.20 times 3.0 kilograms times 9.8 meters per second squared and times 8.0 meters. And it's all divided by K, which is 120 Newton meters. Let's calculate this number. It equals to 0.88 meters. So basically 88.5 centimeter. So that's the solution of this problem. I hope I helped you. Thank you very much for your attention. And yeah, before I stop the recording. Yeah, I just probably forgot to mention that if you want to calculate the correct number of decimal places, maybe we should round it to two significant digits. So that would be 0.89 meters, because of the number of significant digits here and here and here. So anyways, here is the solution. That's the solution of this problem. I hope I helped you. Thank you very much for your attention.